and liftoff.
On the 25th of December 2021, at 12:20 Coordinated Universal Time, the James Webb Space Telescope was launched in an Ariane 5 ECA rocket. This was arguably one of the most important accomplishments in scientific history as a whole. But did you know that this telescope was actually under construction for about 19 years and was under various tests for another 6? Welcome back to another video on the channel, podcast, whatever this is. I know I haven't uploaded in a little bit, and by a little bit I mean 10 months, so you know, that's the thing. Today we're going to be covering one of the most important accomplishments in scientific history, the James Webb Space Telescope. So let's dive right into it. Firstly, how was the telescope created? Well, it was first proposed in 1996 under the name of the Next Generation Space Telescope, and it went under this moniker until 2002 when it actually began construction. As to why it took so long to complete, well, we first need to understand the nature of the telescope to find out why it was under construction for so long. You see, most telescopes are earthbound, which means that any damages and/or malfunctions can be amended on the spot. However, ground telescopes have one big limitation. The resolution of the produced image is not high enough to see distant objects like galaxies and quasars billions of light years away. Factors: light pollution and the atmosphere. You are probably somewhat familiar with light pollution, which is when light from urbanization, i.e. street lamps, car lights, building lights, etc., blocks out the light of distant stellar objects, such as the galactic center. If I show a comparison between these two images, you can see that there's a significant difference between the image with light pollution and the image without. Another problem is that these telescopes are ground-based. Because there's quite a bit of air between the view of space and the telescope, this is going to block out some of the light and thus produce a less clear image. There are two solutions to these problems. Scientists often build these ground-based telescopes in really isolated areas, mostly cheating. Because the telescopes are at some really tall summits, there is therefore less air in between the telescope and the sky. Now, the problem of air getting in the way isn't a high priority for observations of large objects, such as nearby galaxies. However, it is detrimental when attempting to observe smaller or more distant objects like stars outside the Milky Way or the galaxies farthest from us. So another common, though more expensive, approach is to ditch Earth altogether and send the telescope to space. The Hubble Space Telescope is one such example. Hubble was built for space, and it was and still kind of is quite revolutionary for the time. Hubble was used to study faraway objects like GN-Z11, the most distant galaxy prior to the observations of the James Webb Space Telescope. This is good for observing some very faraway objects, but as I said earlier, this is quite expensive, like tens of billions expensive. Now, going back to the James Webb Space Telescope, one of the reasons it was even built was because of a very interesting effect that happens with light. You probably know that light has a finite speed, the constant c, which is equal to approximately 300 million meters per second squared. This is exceedingly fast at the scale of our planet, but in the vastness of space, this is quite slow. Like, really slow. In fact, to travel to the nearest star to us, Proxima Centauri, it would actually take 4.24 years to get there, at the speed of light. As a result, the Proxima Centauri you see in the night sky, although you do need a telescope to actually see it, is about 4 years behind in the past. Now, this delay is pretty short, but on larger scales it can get quite long. For instance, the famous Pillars of Creation located in the Eagle Nebula, about 6,500 light years away, is actually already been turned completely into stars, because it's actually a stellar nursery. However, the light from the pillars is so old that we're seeing them how they were 6,500 years ago. This delay between the origin of some light and the recipient to that light is known as time dilation, and is one of the key components of Albert Einstein's theory of special relativity, which outlines the relativistic nature between time and space. Now, where is the usefulness of this? Well, by using this technique, you can essentially look backwards in time to how the universe was possibly billions of years in the past, which is really good for understanding and confirming our models of galaxy formation. Up until the creation of the James Webb Space Telescope, the furthest that we could see using the Hubble telescope was about 13.6997 billion years ago, about 300,000 years after the Big Bang. We, as a result, learned a lot about early star formation and galaxy formation, which had so far kept up with our models. Now, Hubble was built to orbit Earth. In the case of a mistake was made during the construction, or an accident occurred in space, for instance an asteroid crashes into one of the mirrors, and NASA would have to send astronauts to fix it. This actually happened right as the telescope began taking images. The produced photographs came out blurry due to an error in its mirror, so NASA sent astronauts to go fix the issue, and the problem was solved. Because the margin of error was larger for Hubble, there was more leisure in the building process. I should note, however, that Hubble also took about 20 years to come to fruition. You have to keep in mind, however, that it began construction in the 70s and was launched in 1990. The internet wouldn't even surface for another 3 years. However, because the telescope was going to be close to Earth, it would still be problematic if scientists wanted to see the universe further back in time than 300,000 years after the Big Bang. This is why the James Webb Space Telescope was launched to orbit the Sun instead of the Earth. There, no air would obstruct the view of faraway objects, and the problem would be solved. But this solution did come at a cost, because that meant that now the telescope couldn't be fixed if there was an error. Furthermore, the telescope was more advanced than others of its kind, with the primary mirror composed of 17 smaller hexagonal mirrors with a sheet of gold. The infrared optics mechanism is also quite complicated, as you can see in the diagram here. So it needed to be folded first, then in space unfold and begin photographing. So as you can see, it's a pretty complex procedure. So it would only be just for the 1,200 people who worked on the telescope to be a little anxious. The telescope was finally completed in the fall of 2016 after 2 decades of construction, but it still had another half a decade of tests and experiments to check if all the instruments were functioning correctly. The telescope's launch date was infamously delayed many times. So many times I can't even cover them in this video. Here's a list of all of them, however, just in case you need some sort of reference, which I definitely did not steal shamelessly off of Wikipedia. Anyway, I actually still remember in 2018 when the telescope was set to launch in 2020, but that ended up getting pushed back due to some issues, and was now set to launch in October of 2021. The telescope was finally ready for its long-awaited launch, but it had a problem, as the James Webb Space Telescope was notorious for at this point. This time it wasn't with the telescope, but with its rocket, the Ariane 5 ECA. The high-altitude winds created a bit of a hiccup in the launch process, but in Christmas Day of 2021, the telescope finally launched into space. But the telescope still had to be unfolded. So for the next month, the rest of the world stood anxiously as they watched the telescope unfold in space. Luckily, everything went as intended, and the telescope was ready to take its long-awaited images. The first image taken by the telescope was not actually a science image, but was actually a test to see if its alignment mechanisms were working properly, and it resulted in monumental success. At first glance, the image looks quite unappealing, just a star with some other objects in the background. But it's these background objects that are the real attraction. Every single one of these objects is a galaxy, millions of light years away, visible even with a star in the foreground. You might also notice the image is kind of red. That's because it was taken with the infrared objects and not the visible light ones. The first actual science image captured by the James Webb Space Telescope is actually the same exact scene Hubble photographed in its famous ultra-deep field. When I show these two images side by side, however, you can see that there are more galaxies in the James Webb photo than in the one Hubble took. Other than the fact that there are more galaxies, the most prominent feature is the quite apparent gravitational lensing occurring in the center of the image. If you aren't familiar with this cosmological effect, gravitational lensing is essentially the magnification of incoming light from other objects behind some really large object, like a cluster of galaxies, for instance. And this actually helps us see further objects better because it's magnifying them like basically a gigantic telescope in space. Since the first science image that the James Webb Space Telescope took, we've gotten many more images to look at, and we're going to cover some of the best ones here. This is an image of the Southern Ring Nebula in the constellation of Vela. We also have an X-ray version of the image on the side. Now, if we zoom in on the top left corner, you might be able to see a linear figure right here. At first, you might think this is some artifact from the camera, or maybe even a streak of gas from the nebula, but this is actually a very thin galaxy whose edge is pointed nearly directly at us. This is a very rare occurrence as most galaxies facing us are often at an angle of some degree. So for its galaxy to be essentially perfectly edge-on with the Earth is quite surprising. This composite image displays Stephan's Quintet, a group of 5 galaxies in the constellation of Pegasus. The cluster of 4 galaxies highlighted here is situated at a mean distance of 300 million light-years away, while the galaxy NGC 7320 on the top left corner of the image lies some 39 million light-years away. Arguably the most eye-catchy object here is NGC 7318, a pair of galaxies, NGC 7318A and NGC 7318B, merging with one another about 280 million light-years away. Right here we have the Tarantula Nebula, an astronomical object located outside the boundaries of the Milky Way, instead in the Large Magellanic Cloud, at a distance of about 163,000 light-years. In the central region of the nebula, you might be able to see a very dense cluster of mostly blue stars. This is R136, the most concentrated section of the star cluster NGC 2070, located in the nebula. The nebulous gas that you see here is actually ionized by the radiation from all the stars in the nebula, and it creates something known as an emission nebula. This is also the home of the most massive star that we know of, R136A1. Located in R136A, a collection of 8 stars in the center of R136, R13681 has a mass of about 196 solar masses. In other words, it is 196 times more massive than the Sun. This image is the sharpest of R136A and subsequently R136A1. These sort of stars are more akin to amorphous blobs of gas and plasma rather than the more tightly spherical shape of other stars like our Sun. R136A1 is no exception, as it expels about 321 billion tons of mass per second via stellar winds. The star is likely formed by a merger of some stars due to the large concentration of stars in the area. R136A1 is about 1 million years old, which is actually pretty deep into its lifespan since these types of stars don't really last long. As such, astronomers expect R136A1 to last another 3 million years before it goes supernova, and it will likely turn into a black hole given its incredible mass. Here, we don't have an image, but instead some graphs of data collected by the James Webb Space Telescope about the exoplanet's Boca Prints. Discovered in 2011 by the Wide Angle Search for Planets, or WASP, Boca Prints, formerly WASP-39b, is an exoplanet 700 light-years away from Earth. Although the WASP telescope discovered it first, the James Webb still observed the planet transit its parent star, WASP-39. The telescope also, and most significantly, collected high-quality spectra, which showed that the planet's atmosphere was mostly carbon dioxide. Spectra are essentially analyses of light coming from the planet, where it's divided into different sections of the visible light spectrum, and given which part of the spectrum the planet has more of, astronomers can essentially assess the type of atmosphere that the planet has. In the case of Boca Prints, there was a substantial amount of carbon dioxide in the planet's atmosphere. This went in slight contrast to a 2018 study which assessed the presence of water vapor in the atmosphere, possibly a disequilibrium in its chemical makeup. Spectra was collected from the light that came from the star that diffracted during the transit. Depending on the chemical makeup of the atmosphere, the light entering the atmosphere reacts differently. In this case, the difference in brightness in infrared imaging, which is essentially the difference in color, shows what the atmosphere is made of. This image is of the current record holder for the most distant galaxy we know of, Cheers 93316. Although it is not yet confirmed, the galaxy may be as far away as 34.684 billion light-years away and as old as 13.667 billion years, near the limit that the James Webb can observe. There's not really much to state here, other than the fact that it does kind of meddle with galaxy formation models a little bit. In this lovely image, we have the Pillars of Creation mentioned earlier. This is the most recent image at the time of recording this video. It was actually captured on July 29th of 2022, but was officially released on October 21st of 2022. If I show the previous image of the pillars taken by Hubble, you can see that the James Webb image contains many more stars than Hubble's. This is partially because the James Webb is simply more advanced, but mainly because it is a composite image, so the infrared layer of the image can view the stars behind the gas. Lastly, we have these images taken by both the James Webb and Hubble telescopes of the conclusion of the DART mission. Conducted by NASA, DART is a mission to defer potentially hazardous asteroids that come a little too close to home in a quite literal sense. What we are seeing here was a test of DART's capabilities, which ended up proving to be quite satisfactory. The object tested on was Dimorphos, the moon of the asteroid Didymos. The mission involved sending a spacecraft to the target at incredible speeds, so that the target could defer from its original path, thus potentially saving Earth from an impact. The mission did not disappoint, as Dimorphos' orbit decreased by about 32 minutes, which is quite remarkable. After the impact between the spacecraft and Dimorphos, both the Hubble and James Webb Space Telescopes captured photographs of the moonlet, as well as its very lengthy trail of debris ejected during the impact. This one is definitely for the history books, and probably warrants a video itself, so stay tuned. And those are some of the major discoveries and observations of the James Webb Space Telescope. If you enjoyed this video, then make sure to leave a like. If you like the content on the channel, then subscribe. Make sure you turn on notifications so you don't miss when I upload again. I'm sorry I haven't uploaded in a really long time, like a really long time. These past few months really flew by a lot, as there's been a lot of stuff happening recently. So make sure to stay tuned when I upload again, which should hopefully be soon. Nevertheless, as always, my goal is to feed your brain.